Alright, welcome. In this video we're going to be talking about logarithms, a long-awaited topic in Algebra 2. So we talked about exponential functions, and logarithms go hand in hand with exponential functions because that's how we're going to solve an exponential equation. Alright, so we're going to start off right where we started off in the last lesson. We're going to find some values of f of x equals 4 to the x, and we're going to sketch the graph. Let's get that in. Alright, there we go. Made a table, plotted points, connected the dots. Pretty rough as sketches go, but you know, it'll do. I'm going to bring in a y-axis here, and let's see. All right, let's go about here and down there. Okay, that's going to be my y-axis. I'll label this with 1 because that's the y-intercept, but that should be good enough for our purposes here. Okay, now next I'm going to zoom back in and say, all right, what are the values of x where f of x is equal to 2? Well, 2 would be, like right about there. And if I went over, okay, said that's 2, went over to where the graph has y coordinate 2 and looked down, that looks like x equals 1/2. Okay, so let's think about that. F of x equals 2 would be when 4 to the x equals 2. And the square root of 4 is equal to 2, so if I put the 1/2 power on there, I'm taking the square root. That makes sense. Okay, so I'm going to say x equals 1/2. All right, f of x equals 8. Well, let's see. I'd say that's about right here. I don't know, that's kind of a guess. But then I go over, I find on the graph where the point that corresponds to y equaling 8, and I look down, and so that's between 1 and 2. A good hypothesis might be 1.5, for the x value that would get me here. So 4 to the x equals 8. But maybe I'll just solve this one using the techniques we used in the last lesson, right? Write both of these things as a power of 2. 4 is 2 to the 2. 8 is 2 to the 3. All right, so this is 2x equals 2 to the 3. And we got the same base. Now we can set these things equal to each other, and I'm going to say, all right, well, this is 2x equaling 3. X is 3 divided by 2. That's 1.5. Right. Find the values of x where f of x equals 1/2. Okay, well, if it's below y equals 1, and I'm looking at it's going to come over here and it's going to return me a negative value of x. So I should expect to see a negative value. So 4 to the x equals 1/2. I think I'm going to use the same technique I used over here, right? Both of these is a power of 2. So 4 to the x is 2 to the 2x. We can kind of skip that step. And 1/2, that's 2 to the negative 1. So 2x equals negative 1. X equals negative 1/2. Okay, and that seems reasonable. Looks like it's going to hit somewhere there. Right. F of x equals 1/64. Okay, well, let's just get to it. 4 to the x equals 1/64. Okay, 64 is 2 to the 6th power. So this would be 2 to the negative 6. So 2 to the 2x equals 2 to the negative 6, meaning 2x equals negative 6. I think x is going to equal negative 3. And finding the values of x where f of x equals negative 4. That would be where 4 to the x equals negative 4. And I'm going to say that this is not possible. This equation has no solution. And not just because you don't have the techniques needed to solve it. It's not possible to take a positive number like 4 to a power and get a negative number back. Also, look at the graph. We can see that everything's been positive. The farther I go to the right, the farther up the graph goes. Farther from negativity it's going. And then as I move to the left, as x approaches negative infinity, 4 to the x is approaching 0 because it's like, I'm taking 1 over higher and higher powers of 4 as x gets more and more negative. Either way, those are positive numbers. Those aren't negative. It's not negative 4. Same thing here. 4 to the x equals 0. This has no solution. Because, I'll just write in the fact right here. Yeah. So the key thing here is that if we've got a positive number and we take it to any power, that's going to also be positive. And then the last thing here is kind of getting us towards what we need to talk about today. Where is f of x equal to 100? Where does 4 to the x equal 100? I don't know. Okay, 4 to the 3 is not 48. I'm a little embarrassed, but I can't. I'm too far in. I'm not going to re-record this. 4 to the 3 is 64. Okay. think it would have been a better question if I'd asked where's f of x equal to 50, then I could have actually been on my sketch or something, but it wasn't, so whatever. Who cares? So 4 to the x equals 100. Well, 4 to the third is 64, and 4 to the 4 is 256. I'm just going to... Okay. So 100 being between 64 and 256 on this increasing function, okay, is going to come at an x value that's between 3 and 4. Okay, so x is between 3 and 4, but we don't know much else at this point. We're going to need the logarithm tool to be able to figure that out. All right, now let's just talk about these logarithms and get ourselves a definition of a logarithm. So a logarithm is an exponent that produces a desired result. And the formula, it's not even really a formula, it's two equations that are equivalent to each other. So we've been talking about exponential situations. So we've got a base of our exponent, an exponent, and equaling some number, which maybe I'll call A, like an answer or something. And that's going to be equivalent equation log base b of a equals x. So when we're talking about a log, we're talking about the exponent we need to use to get this result. So what exponent am I putting on b to get a is log base b of a. Okay? And then what I'm going to tell you, the piece of advice that I'm just going to be repeating over and over this unit, the next, really throughout this course, is that the log is the exponent. Right? It's the special exponent, but at its core, it's just an exponent. Okay? Not anything worth being scared of. So over in the previous example where we were tasked with solving 4 to the x equals 100, we were like, okay, I don't know. It's between 3 and 4. Oh, whoops, I forgot to use technology to determine x is 3.3219. Let me show you how you would do that. All right, so I pulled out my technology. I've typed in y equals 4 to the x and y equals 100, and I'm going to graph. I'm going to actually manipulate the window so that, because I need to be able to see y equals 100, I'm going to go from negative 10 to 150, and I'll set the scale at 10. Okay, so there's my exponential curve 4 to the x. There's y equals 10. I'm going to be interested in where they intersect, right? So I calculate the intersection. We've done that in this class a couple of times. First curve is going to be the blue one. Second curve is going to be the red one. Give it a guess. There's only one intersection. Okay, so that's where we see x is 3.3219. Okay, and so that's going to be the value of x that works. But that's just an approximate value, right? We can see that there's more decimals, and if we need to be more accurate, 3.3219 might not be accurate enough. So the exact value of this is, okay, if we've got 4 to the x equals 100, I'm copying it again. Okay, 4 is the base, and 100 is like the answer. Okay? So that means that x is going to be equal to the log with base b, log base 4 of 100. Okay. Now, I'll show you on the calculator. This is a no calculator class, and a no calculator unit within a no calculator class. But, it's occasionally useful, and I kind of probably think I should show you about this feature that some of the TI-84s have if you have the new software. You press math, and then you go up from frac and to log base. You press log base 4 of 100, and then you're going to get that same number again. So I was just going to point out to you that's how that works. We can do that. If you don't have that log base key, I'll show you a different way in the next lesson for you to evaluate logs on the calculator. But I'm also saying, even if you do have a nice calculator like that, you should not be using it on today's homework, right? Or really on any of these log things, because I need you to be able to do all this stuff without a calculator. All right. So now, some logs related to 4 to the x. I'm going to do a few of these, and then I'll say, all right, probably the last of them I'll let you try to figure out on your own and check your work against mine. Okay, I'm going to even copy in the fundamental question on the first one. What exponent am I putting on 4 to get 16? Okay, and I'm going to sit there, I'm going to think about it for a second, and I'm going to put the 2 exponent on 4 to get 16. So this is going to equal 2. What exponent do I put on 4 to get 64? 4 to the 3 is 64, so log base 4 of 64 is just the exponent I put on 4 to get 64. Log base 4 of 4, what? Put on 4 to get 4. That's the 1 exponent, because the first power of something is just that. Okay, 4 to the what equals 1 over 4. And so now you might see we're going to really be kind of focusing in on these exponent rules that we've been learning about really in the whole class. So log base 4 of 1/4, what exponent I put on 4 to get 1 over 4, that's going to be the negative 1 exponent. Okay. And then over here, okay, log base 4 of 1, okay, what exponent do I put on 4 to get 1? That's going to be the 0 exponent. Okay. And I'm going to point out, I think later in the video, that log with any base of 1, log of 1 is always 0, regardless of what the base is. Okay. Now, with these last ones, I'll show a little bit more work than I've been showing up to this point, but I want you to try these on your own. Pause the video. You know, give it a hypothesis. Worst case scenario, you're wrong, you scratch it out, you put in the right answer, right? Very low stakes here. So you should do that now. I'm going to bring in the answers in 5 seconds. All right, there you go. So you see these, and I think these were all ones that we worked on the previous page when we were making that graph. Okay, and I don't know if you put that together, but if you didn't, go back and look, and you'll see that you kind of solved all the same equations. Okay, for this one, I'm saying, okay, what exponent do I put on 4 to get 2? The square root of 4 is equal to 2, and the square root's the half exponent. Okay, so I'm putting the half exponent on there. You could also set it up as an equation, right, and solve that, kind of the way I did on the previous page. Or you could just think about it. What exponent do I put on 4 to get 1 over 16? Well, I put 2 exponent on 4 to get 16. 1 over 16 is 4 to the negative 2 power. And then keep it on going. And then we said that those equations didn't have any solutions, so these logs are undefined, right? Because there's no power I can take 4 to get negative 1. There's no exponent I can put on 4 and get 0 back. That's just not going to be possible. All right, so compute the logarithm. Log base 2 of 1/8. All right, so I'm going to set up I don't know if I'm not going to call it an equation, right? We'll solve these equations a different day. 2 to the what power equals 1 over 8? Okay, 8 is 2 to the third, so this will be negative third. The negative third power. Okay. I'm going to put a little arrow because I wouldn't want anybody to think that this is equal to 2 or something like that. For log of 1,000, wait a second, this doesn't have a base on there. All right, so I need to tell you, because about logs at this point, that if you don't see a base, it's implied to be 10. Okay, for I don't know, science reasons, really. I don't know, you take the log of a number, like the common log, that's what we call it, where there's no base, the common log of a number. It does tell you, like, how many, like, how many decimal places it has, kind of. Or, what power of 10 you have to take. So it has to do with, like, how long the number is, basically. Anyway, I'm saying 10 to what power equals 1,000? 10 to the third is equal to 1,000, so this log is going to equal 3. Yeah, that's going to be better. And then over here, I'm going to say 5 to what power equals 1/5? Exponent am I going to put? Oh, negative 1 exponent. Okay, so I say that's equal to negative 1. Okay. Log base 7 of 49. I'm going to ask myself, what exponent do I put on 7 to get 49? That's going to be the 2 exponent. I think we can do that one without setting up an equation. What exponent do I put on 16 to get 4? 4 is the square root of 16, so that's going to be a 1/2 exponent. And then this one, okay, maybe you don't see that. This guy's square root is the base. That's pretty atypical, but, we can work with that. All right, so here, I'm going to say square root of 3 is the base. To what power equals 3? Well, it had to be to the 2 power, right? Because I square this thing and I get rid of the square root. All right. And now we're going to write the exponential equation as a logarithm. Now I'm going to do 2 of these, and I'm going to ask for you to do the other 4, right? But this is definitely like the type of question that you might see on the quiz next time, or on the test at the end of the unit. So 6 to the 2 equals 36. We need to copy in the definition of a log. All right, so when we go to convert the exponential relationship to a log equation, okay, the base of the exponential becomes the base of the log. So I'm just going to say, all right, I'm going to go over here. This is a log with base 6 of something, well, the log is the exponent. This is what I'm saying. The log is equal to the exponent I put on. Okay, so that's going to be 2. And then the 36 just fits right there. But you can see that, the answer here is what goes on the inside of the log. It's the argument of the log. Okay, and then I'll do this one. This one's very similar. It's just wait, no, I'm doing this one over here so that we had, one where the exponential thing was on the left and one where it was on the right. I don't know what else to do. So I'm going to say log, base of the exponential is base of the log. The result goes on the inside, and the log is the exponent. Okay, and then, you try the other 4. Okay. Give these a shot. Now, like the square root of 121, you might have to write that as 121 to the 1/2 power, but that's something I expect you to be able to do now. And so I'm going to, you do this on your own. I'm going to bring in the answers in just like 5 seconds. All right, there you go. So I really just kind of approached these the same way as I did the first 2. I think that y'all probably would be good with this. At least students in my class this year seem like they're pretty good on this type of stuff. Now, writing the logarithm as an exponential equation. Okay, this is going to be the exact same thing in reverse. So let me copy in the rule. So let's just get to it. I'm just going to do the first 2, and then I'll let y'all work the rest of them, and I'll, flash up my answers and give any commentary I've got. All right, so here, the base of the log becomes the base of the exponential. So 3 to some power, well, the log is the exponent. So the log is equal to 4. That's going to be the exponent of 4. That's going to be equal to 81. This is true. This makes sense. Okay, so like if you're going and doing the rest of these, and you're getting some equation that you are unsure of if it's true, you should probably double check your work. Okay, this one, the base of the log becomes the base of the exponential. So 2 to the negative 5 is equal to 1 over 32. Because what this is saying, log base 2 of 1 over 32 equals negative 5, is that if I want to take a power of 2 and get 1 over 32, I have to put the negative 5 exponent on there. It's like a special exponent finder. All right, so you are going to work these 5 on your own, try to write an exponential equation, and then check your work against mine, which will come up here in just a few seconds. All right, there you have it. So I'd say that I didn't see anything weird. I saw, some things come up in these that is like, 2 to the 2x equals 4 to the x. We had talked about that, and b to the 0 equals 1. I felt like there was something else, but anyway, the only other thing I have is that this is true for any b. Really, it's true for any b that's suitable to be the base of a log, which is going to be b is not, it's not a negative number, it's not 0, and it's not 1. So really any positive number that's not 1 is a suitable base for a log. Okay, but I think that's all I got to say about that. Let's move on. All right, next I want to tell you about the natural log. Okay, and if I'm being honest, that's really the only type of logarithm that I care about at all. And really the same way, right? For reasons that will become much more obvious in pre-calculus and really in calculus, you'll see why we really only care about natural log and only really care about exponential functions that have base e, but more discussion on that in the future. So the definition of natural log of x is that if we've got e to the x equaling some answer, then that's equivalent to saying that the natural log of a, and we say natural log with an L and an N. I usually write this kind of like with a script, but ln of a is equal to x. Or you could look at the kind of the definition of natural log is that natural log of x is equal to log base e of x. That's kind of what we're saying there. Okay, just been looking at it. Okay, so compute the log. Natural log of 1. Okay, natural log of 1 is what exponent do I put on e to get 1? Okay, and so our level of responsibility with natural logs is actually pretty low. Okay, we can figure out what the natural log of 1 is. That's going to be 0. I just told you that was true for any base. Okay, so natural log of 1, common log of 1, any log of 1 is going to be 0. Okay, natural log of e. Okay, e to what power is equal to e? That would be the first power. Okay, what exponent do I put on e to get e to the 10? This is not a trick question. I put the 10 exponent on there. Okay, e to what power is 1 over e? Okay, well, that would be the -1 powers. The same themes coming up over and over again. And natural log of cube root of e. What exponent do I put on e to get the cube root of e? That's going to be the 1/3 exponent. Okay, so that's just how the natural logs are working. What do these logs mean? Okay, this means log base e of 5 is approximately equal to 1.61, meaning that, okay, base of the log is base of the exponential. Argument's the answer, or pardon me, yeah, the argument's the answer, but I was pointing at the log, and that's the exponent. 1.61, not 1.65, pardon me. That's equal to 5, or I guess about equal to 5. And then over here, it's going to be the same thing. E to the 3 is approximately equal to 20. Is that true? I don't know about that. E to the 3. Oh, very close to 20. Yeah, sure enough. All right, now sketching the graphs of log equations. What I'm going to do for now, we'll come and talk about this more when we talk about inverse functions and all that stuff. The graph of natural log and these log functions, I'm thinking, yeah, we do need to graph these in Texas Algebra 2. I went and double checked, but I'm telling you, it's not going to be the most important thing we do in our Algebra 2 class this year. Okay, so I'm going to show you we've seen already that the log of 1 is always equal to 0 regardless of the base. So at x equals 1, log base 4 of 1 is going to equal 0, so my x-intercept will be x equals 1. Okay. We've also seen that if we're trying to take 4 to a power and get a number that's less than 1, like a fraction, it's going to be a negative exponent. So what's happening here is that the graph is going downhill. Now, this function is undefined at x equals 0. We've already talked about how the log of 0, and we've actually specifically talked about how the log with base 4 of 0 doesn't exist, because there's no exponent I can put on 4 to get 0. Okay, and then it's going to increase, though, because I want to get 4 to the what equals x. If I'm trying to get a bigger result back by taking bigger powers of 4, I have to put bigger exponents on. What's going to happen is it's going to really grow slowly. And maybe you noticed kind of like the relationship between the graph of y equals x squared and the square root of x. It kind of looks like an exponential function that's been turned on its side somehow. And there will have a lot more to say about that. I think the only other thing I can say about log base 4 of x is, okay, well, when x is equal to 4, y is equal to log base 4 of 4. It's like, okay, what exponent do I put on 4 to get 4? That's the 1 exponent, and that's going to equal 1. So the 0.4, and 1, that's supposed to be a tick mark, is also on the graph. So for our graphs of log equations, we're going to be displaying like the vertical asymptote. We're respecting that behavior. We got the shape of the graph, and we got the x-intercept and 1 additional point. That should be good. Okay, and then natural log x, I'll go a lot faster on that one. It's going to have a very similar shape. Probably can't even tell to the naked eye, especially when I'm sketching. But I need to figure out when does y equal 1? 1 equals natural log x. Okay, and we're not really solving exponential equations yet, but what you can always solve an exponential equation or a log equation by going back to the definition of a logarithm. Okay, that it does work. So that's 1 is log base e of x. Okay, remember, we've done this, turn this into an exponential relationship. The base of the log is the base of the exponent. E to the 1, because the log is the exponent, e to the 1 equals x. So x equals e to the 1. Okay, e is between 2 and 3, so I'm just going to put that right there. Okay, and then that's going to be 1 unit up there. Okay, and that's the graph of y equals natural log x. Notice, it looks exactly like log base 4 of x. They're all kind of in the same family. So, all right, domain of a log function. Okay, we've seen evidence of this, and I'm just going to tell you the fact is that log base b of u is defined only when u is positive. And by u, I could mean something like 2x plus 18 or x squared minus x, that type of thing. So let's really, I think the important thing is kind of like we did this with square root functions. We're going to grab the argument of the log. We're going to grab the inside. And we're going to set it greater than 0. So for this one, the domain is going to be, I grab 2x and 18, and that's going to be positive. Got to be greater than 0, right? Because I can't take the log of 0 and I can't take the log of a negative number. And then I'm going to solve. 2x greater than negative 18, x is greater than negative 9. Okay, now I think it would be good for you to practice these other ones. I'll set up the inequalities. You try them on your own. So this one, it's been a while since we solved a quadratic inequality. We really struggled with that in my class this year when we learned about them. Okay, so why don't you try these on your own with the video paused and check your work against mine, which is going to pop up in about 5 seconds. All right, there you go. So, these two are pretty straightforward linear inequalities. We have a lot of experience solving those. We've done a lot in the class. Quadratic inequality, remember, you factor, and then you have to sketch a graph. And if we're looking for where it's positive, okay, we're going to need to see where the graph is above the x-axis. And that was where x was greater than 1 or where x was negative. Okay, so let's go in and talk about these fundamental identities just to wrap up with, right? Let me make sure. Yeah, that's going to be all. So with the fundamental identities, these are really important. I'm going to be using these really, really regularly for the rest of the unit. Okay, so the log base b of b to the x, that's equal to x. And now you can just remember as log and exponential are not reciprocals, but they're inverses of each other, so they kind of cancel each other out. But I think it's better to say, okay, log base b of b to the x. Remember, the log is the exponent. And this is saying, what exponent do I put on b to get b to the x? Well, I put the exponent on b, and I get b to the x. That's what I would expect. And same thing over here, natural log b to the x, that's just going to be x, because natural log b to the x, okay, natural log is like what power do I put to e to get e to the x? Okay, well, it's just x, right? And, okay, then this one's a little trickier to think about. Okay, so if I take b to the log base b of x, remember, log base b of x is, and I'm going to just write this out in words, it's the exponent we could put on b to get x. But I'm putting that exponent onto b right there, and so I should be getting x, right? And same thing over here. Natural log of x is the special power of e I take to get x. So if I take e to that special power, I should get x. And those are the fundamental identities. Okay, these are going to be really important. I will talk with you about these at length, really, in class for the rest of the unit, if you need, for the rest of the year, because this stuff's really important. So thanks for watching with me today. This video took more than I normally like to spend for these Algebra 2 videos, but this is so fundamental that I think it's worth it. So thanks for your time. Thanks for being here. I hope this helped.